Good morning, everyone. So I'm back with this question. Okay, so last time I figured out the R, which is 0.24. Right? Okay, so I'm just not going to do that again. Okay, 5 is 65. Okay, so now the current is equal to 65 milliampere. Milli means times 10 to the minus 3 amperes. Okay, so for this type of structure, we know that the equation is equal to B equals to mu naught I over 2R. It's not 2 pi R, that is for a straight wire, it's 2R. So here, using this equation that we just talked about, so mu naught is 4 pi times 10 to the minus 7, your I is 65 times 10 to the minus 3, and then your 2, and then 0.24, which is your radius of the coil. So you will get the B as equal to 1.7 times 10 to the minus 7 Tesla. And where is that B? Where are we? We are trying to find B, but B is like everywhere, right? Where are we actually trying to find the B? So the B always refers to the center, the point at the center of the coil. You need to remember, when you are talking about a straight wire, the B that we are looking at is the R, a distance R from the wire. So this forms the circle. So I'm trying to find the B around this circle. So for the coil, I'm trying to find the B inside the coil. Okay? So I hope that is clear. Moving on. This is the next example. A wire 1.5 long. Oh, this is the same one. Apa? Macam sama. Oh, lain 65. What is the center? R is the circumference magnetic field at the center of the coil. Magnetic field at the center of the coil is... Oh, sorry. This is 50 turns. Okay, it's a different question. Previously, this question only N is equal to 1. So the coil, number of turns of the coil is only N equals to 1. So we omitted it from the equation. Now when the coil is 50 turns, so 1, 2, 3, 4, blah blah blah, and it should be equal to 50, and then only this is the coil lah. Okay, it looks like cotton candy, but it's a coil, which the N is equal to 50. So the equation is the same equation, mu naught I over 2R, but since the N is not equal to 1, we need to have it in the equation. So this is 50 times mu naught times I divided by 2R. Now we want to find the new radius. Remember, we are using the same length, but now instead of making one coil, this is 1.5, this total is 1.5. Now it's split into 50 turns. It's split into 50 turns. Previously, we talked about 1.5 is equal to 2 pi R. Now, the equation is 1.5 is equal to 50 circles or 50 circumference. So now the R is different. The R is, whatever that is 4.77 times 10 to the minus 3 or 4.77 millimeter. Kecil lah. Kan? Bila kita ada same length, when it's only one, besar. Bila kecil, bila banyak, jadi kecil lah. It's like real stuff. I mean like real world examples. Okay, so that R kita dah jumpa, and then find the magnetic field at the center of the coil. So using the equation that we talked about, N mu naught I over 2R, the R is going to be smaller because the number of turns is not equal to 1. Okay, so that is your answer. It's easy. It's just understanding how to use the equation and how to find the radius, right? Okay, so we are talking about Ampere's law. Ampere's law forms all the B equations that we have seen so far for the straight wire conductor and also for the coil. So Ampere's law is about, for any closed loop path, the sum of the product of the length elements, okay, the sum of the product of the length elements, which is L, and the magnetic field, which is B, in the direction of the length element, maksudnya along the loop or along the path, is equal to the product of the permeability mu naught and current I. So we have seen this part before. Mu naught times I over 2R. Mu naught times mu naught times I over 2 pi R. We have seen this before. So what we have seen so far is B equals to mu naught I over 2 pi R and mu naught I over 2R. So here, let's look at this equation. Mu naught I times over 2 pi R. So this is actually the path of the loop when the loop is a square, right? So basically, this equation comes from Ampere's law. So B times 2 pi R, which is the circumference of the loop, the circumference of the circle, which is B, which is the magnetic field punya, the electric field, equals to mu naught times I, which is the same as the sky actually. And sama juga macam coil. So the equation for coil is also from Ampere's law. So basically, Ampere's law says that the product of B with the length elements, or the length of the loop or the length of the path, is equal to mu naught I. So this forms the equation for our straight wire conductor and also for our coil so far. We will see other structures after this, and it is also based on Ampere's law. So Ampere's law ni sebenarnya is a type of integration. As you can see here, there's a sum. So sum ni selalunya akan related to integration. However, we're not going to cover up until the integration part because we'll learn that in advanced physics or physics degree. Okay, it's pretty interesting, but it's not going to be covered in the syllabus. Okay, so that is how Ampere's law is related to our equations for magnetic field. Okay, so B in this loop or in this direction of the path is equal to mu naught I, and I is the current in the conductor or in the coil. Okay, and mu naught is related to the environment, and we just use a constant value for that. Moving on. So here I'm going to besarkan sikit. Okay, hope that you can still see. Okay, never mind. Okay, so this is our next slide. Ataskan sikit. Oopsie. Okay, so magnetic field of a solenoid. This is our third structure. We have seen two other structures. So magnetic field of a solenoid. If a long straight wire is bent into a coil, right? So we're talking about coil. Structure number 2 was also about a coil with several turns. This one, a long straight wire is bent into a coil of several closely spaced loops. The resulting device is called a solenoid. Now, what is the difference between the coil in structure number 2 versus structure number 3? In structure number 2, let's see. Structure number 2 is this guy. This is our structure number 2. We can see that if I have... Okay, so looking at structure number 2. Okay, this is structure number 2. So even if my structure number 2 has several coils, this coil is super close together that the L is negligible. Maksudnya, the coil is so close together that basically the L is not significant. Whereas for a solenoid, let's see, for a solenoid, this is a solenoid, the L cannot be ignored because the L is some length. It may be like the length of a ruler or the length of, I don't know, it's a length lah. It's not small. It's not small enough that we can ignore it. It's a length. Okay, so that is the difference between a solenoid and a coil. Even though the coil has many turns, the coil will not have a length that is long, so we can ignore it. Okay, so for a solenoid, B equals to N mu naught I, where N is equal to capital N over L. So N is the number of turns. So N is the number of turns, and number of turns, and L is the length of the solenoid. Length of solenoid. So the equation is pretty easy. So let's see. Structure number 1 was B equals to mu naught I over 2 pi r. This was a straight wire conductor. And then number 2 was a coil of several turns, and mu naught I, if the coil has only one turn, then n equals to 1, 2r. So this is structure number 3, where B is equal to this guy. Okay. So n, capital N, mu naught I over L. So basically this 2r now becomes L. Okay, so I wouldn't suggest memorizing the small n mu naught I, because nanti takut tertinggal the length. So just remember n, capital N, mu naught I over L. Okay, so this is how the magnetic field of a solenoid looks like. So a solenoid behaves like a battery. So when you start flowing current in the solenoid from here to here, okay, from up here to here, right? The solenoid behaves as if it's a magnet. This is a battery, it's a magnet. So here, this is your north pole and this is your south pole. How do we determine which pole is which, right? So using your right hand rule, again, you curl your fingers in the direction of your current. So here, let's see, the current goes from here to here. So I am looking from this angle, this is my eyes, right? So I am looking at this eye over here. So the eye is going down, going up, down, up at the back and then down, up at the back and then down, up at the back and then down. Okay, and then this is what I'm seeing from the front part of the solenoid. So solenoid ni lingkaran kan? So what I'm seeing from the front is the current is going down, and if I'm looking from the back of the solenoid, the current is going up. So if I'm seeing the current is going down from where I'm standing, this is the solenoid. I am looking at the solenoid. The current flows from here, and then it goes again. I'm seeing the current I going down from my angle, right? So my fingers should point in the direction of the current. So how should I do this? So here the current goes, let me draw my hand. It's going to be weird, but this is essential. I don't know if you can see, but we will try. Okay, this is my eye. Okay, so my eye looks like this. Nampak tak? Ada arrow tu. Okay, you see? Okay, so my eye is that. This is the direction of my eye. What I'm trying to see from my side over here is the eye is going down. So if I curl my hands like this, I'm seeing, this is what I'm seeing. I'm seeing the current going down. Okay, so the current is going down. This is the arrow. So I start with this. This is what I'm seeing. This is what I'm seeing, right? Okay, so my thumb points towards the north. Points towards the north. Okay, so if you're looking at my angle, so I am seeing the current going down. My thumb is pointing this way. This is my north. Okay. So if let's say we flip the current, this is our new eye, right? New eye. Let's use a different color for that. Let's say our new eye is red. Okay. What is the direction of north now? So with that said, when our direction of current changes, the flow in the loop also changes, right? So the current will go from here, so it will go up, going up, going up, going up, going up. Okay, so from my angle, if I curl my fingers, the direction of current should be going up. Okay, so now, how do I make it going up? So this is my fingers, right? It's the direction. If I want to see the arrows going up from my side. So going up, going up, going up, and then this is the direction of my north. So it's the other way. So you try it yourself. This is the direction of my current. From my side, it's going up. At the back, it's going down. This is my north. Okay, I hope that was okay. So moving on. So when we talk about the equation B, what are we talking about? Where is the B that we are finding? Right, so the B is like all over the place, but which B are we talking about? So the B that we are talking about is the magnetic field is concentrated into a nearly uniform field in the center of the long solenoid. So here you can see that the lines are almost like a straight line over here. Okay, so that's the behavior of a solenoid. That is why it behaves like a magnet. So the field outside is weaker and the lines representing the magnetic field are further apart. So outside the solenoid it's super weak. However, inside it's almost uniform, as if it's a permanent magnet, as if. Thus, the magnitude of the magnetic field in the interior of the solenoid is given by the equation. So when we use this equation, we are actually finding out what is the B inside the solenoid. Okay, so it's always inside the solenoid because outside the solenoid it's super weak. We just want to know what is the B inside the solenoid because that is how we are getting the magnetic properties from this coil or from this solenoid. Okay, so the direction of magnetic field of the solenoid is as the following. I told you, so north always start the magnetic field always starts from the north and ends at the south. Okay, so if you have like loops like this, it should always end at the south. And then in the solenoid, it will go from the arrows will point towards the north because remember it behaves like a magnet. So a magnet always points towards the north, just like the compass. Okay, so pointing out of the north, north to south. Pointing out of the north, north to south. Okay, so here is another example, pointing out of the north, north to south. It's kind of weird, but that is how it is. So pointing out of the north, north to south. Okay, so this is north to south. So we know that this is north, this is south. This is north, this is south. Okay, so here the magnetic field lines of a solenoid are similar to the magnetic field lines of a bar magnet. I told you before, because of the uniform magnetic field lines inside the solenoid, it behaves almost like a permanent magnet, which is the natural magnet. Okay, so here we have anti-clockwise and clockwise. What is this? Okay, so if I'm looking from this angle, right? So this is the direction. This is anti-clockwise. So this is north. Oops. Anti-clockwise. Right? Nampak tak? Bila kita lukis, bila kita menghadap ke sini, we are seeing anti-clockwise flow of the current. Right? So that is referring to the north. So north, the current flow always anti-clockwise. This is another tip. Selain pakai tangan tu lah. And then if I'm looking from here, right, this is my eyes, and I'm looking from the back, I will see that the current flow is like clockwise. And for the current flow in clockwise, it is always referring to the south. Okay, so here dia kasih macam tip lah. So clockwise, clockwise, south. Anti-clockwise, don't know if you can see it, anti-clockwise, it will tell you the north. So the anti, so it's anti, right? Anti-clockwise. So N refers to the north. So if your current flow is anti-clockwise, that is a north. If your flow of current from where you're looking at it is clockwise, that is your south pole. Okay? Dia boleh cuba sendiri. Please try it. Benda ni memang takes time to understand. Okay, so again, I'm going to go over the clockwise and the anti-clockwise. So here we have I flowing in the solenoid. So from this angle, my eyes is over here. What am I seeing? I am seeing that it's going this way. So it's a clockwise. So clockwise always refers to south. Okay, this is south. And then if I'm looking from this angle, like kenapa saya nak kena macam ni kan? Padahal saya tengah buat slide. So my eyes are looking at this angle. I will see this is kind of hard for me to see. Yeah, it's an anti-clockwise. Daripada sini macam ni. Betul, anti-clockwise. So from this angle I will be seeing anti-clockwise. Anti-clockwise. Remember I told you anti and refers to the north. Okay? So that is another way to determine the poles of a solenoid apart from using your right hand rule. The right hand rule, remember, draw your eyes along your fingers. What are you seeing? If the current flow is going down, you are seeing this way. Your north is this way. If your eye, you need to see your eye going up. Look at your eye, it's supposed to be going up. Your north is this way. It depends on the angle of which you are looking at it. Okay, so solenoids and electromagnets. So here it's saying that if a piece of iron is inserted in the solenoid, the magnetic field greatly increases. It's almost like capacitors. So capacitors, if you insert dielectrics, the capacitance increases, right? The capacitance increases. So here, for a solenoid, if you put in another ferromagnetic material inside the interior of the solenoid, you will increase the magnetic properties. Okay, so this you will see this in lab. I don't know if your virtual lab has it. I hope they do because it's very interesting. Okay, moving on. Solenoids and electromagnets. The magnetic field of a solenoid can be increased by. So remember, the equation for a solenoid is B equals to N mu naught I over L, where L is a length. The difference between a solenoid and a coil is that the coil punya length is neglected. So the denominator is different, okay? So here for a solenoid, you can see that if you increase the current, you will increase the B. If you increase the length, you are decreasing B. If you increase the number of turns, you are increasing the B. Okay, so the way that you can improve a solenoid is by increasing the current, or by increasing the number of turns, or decreasing the length. If you increase the length, it becomes weaker. So if you want a bigger B, you need to decrease the length. Okay, adding more turns, wrapping the coil around an iron core. This is the only thing that's not related to the equation. Increasing the current flowing through the coil or decreasing the length. Okay, so look at the equation. How can you increase the B? That is how you should. I mean, if they ask you, hey, suggest 2 things that can be done to a solenoid to increase its magnetic field. So you can increase the number of turns, you can increase the current, you can decrease the length. That is correct. Or you can add an iron core in the solenoid. Okay? And then, so this is the conclusion to our 3 structures. We have seen 3 structures. So this is our first one, a current carrying conductor. It's a straight carrying current conductor. This guy is a coil of N turns. The more accurate way to write this is with an N. Okay, so remember your coil, if it has many turns, please put in the number of turns. And then you have the solenoid, which is your structure number 3. Remember, the solenoid has a length, whereas the coil nipis, so tak ada length. and mu naught I over length. Alright. And then let's talk about electromagnets versus natural magnets. So electromagnets can vary its strength. Remember, electromagnet punya magnetic field is mu naught I over path length. So basically, you can, if you increase the I, you can change the B. If you change the path length, you can change the B. So electromagnets can vary its strength. However, the natural magnet that we always see is fixed. You can't change it. And then pole switching, you can switch its pole. As we've seen before, the current, if you have a coil of wire, and then if you put in I this way, then the north will be maybe this way or here. But if you flip the current flow to be, if you flip it to be the other way, orange. So this is your I, so it should switch the pole as well. So just by switching, flipping the direction of current will give you a different direction of north or different direction of south. Okay, so you can switch its pole, whereas natural magnet is fixed. And then the current source generated by a single large scale current. Remember, if we have a coil, this is our large scale current. We supply that current to the coil, whereas natural magnet is generated by many microscopic currents. Remember, when we have a block of magnet, we are not supplying any currents to the magnet. So what happens is that they have like teeny current flowing to give it the magnetic properties. Okay. And then the most powerful strength according to the National High Magnetic Field Laboratory, electromagnet can be up to 45 Tesla, whereas natural magnet only 1.5. So that is your SI unit for B. Okay, yeah, okay. So example, 1200 turns, so N is equal to 1200, is of length 1.5 meters. So we already know that this guy is a solenoid, so we know the equation that we should use. Determine the current that flows in the solenoid in order to produce a magnetic field of 2 millitesla. So B equals to N mu naught I over L, and this should be equal to 2 times 10 to the minus 3. It's asking, hey, what is the I? Right? So just substitute. If you get the right equation, it should be easy. 1200, mu naught is 4 pi times 10 to the minus 7. We don't know what the I is, and the length is 1.5. So just solve for I, you should get this answer, 1.99 amperes. Okay, so next one. Oh, this is the solution, is it? Oh no, this is the next one. Example 95. Okay, so this is exercise 19.1. A current flow of 3 ampere flows in a long straight wire in air. So we immediately know this is a straight wire conductor. So the equation should be B equals to mu naught I over 2 pi R. And the B that we are looking at is around the conductor. So this is the B. And this is our R. Okay? So a current of 3A flows in a long straight wire. This is 3. Determine the magnetic field. Find B at a point 5 centimeter away from the wire. So this is 0.05 centimeter. Just plug in the values. I as 3, R as 0.05. So this is the exact same thing. So the answer is 1.2 times 10 to the minus 5 Tesla. Okay, so the next one is magnetic field at a center of a circular loop. So this is a different structure now. The magnetic field at the center of a circular loop. So I have a circular loop. This is where the B is. Is 5.6 times 10 to the minus 3 Tesla when it carries a current of 15 ampere. So again, the most important thing here is identifying the right equation to use. So for this type of structure, we know that it is mu naught I. If there is more than one turn, you have to put the N over 2R. Okay, so it's asking what is R. it has given you the I, which is 15 amperes. It has given you the B, which is 5.6 times 10 to the minus 3. And it did not say that it has more than 1 turns. So the N is just equal to 1. Okay, so just use this equation, substitute 4 pi times 10 to the minus 7 times 15 over 2. And then we are trying to find the R, so the B goes down here. This is our B. Okay, so the answer is 1.66 times 10 to the minus 3 meter. Okay, I think that was a little bit fast, but this is recorded, so you guys can just pause whenever you feel like it. So this is the end of chapter 19, subtopic number 1. Okay, so I'll see you in class. Bye-bye.